In the last section, you looked at solving systems of equations graphically, and now what we're going to do is use the algebra and solve them that way. So maybe we don't have any graph paper, maybe it just takes too long. You can't always be really exact, so if you had fractional places where they intersect, it just doesn't work very well. So we need another method for solving systems, and let's just start off with a review then of how many solutions you can have. So remember, if you have two lines that are parallel, then a solution is you're looking for the points they have in common. Well, they don't have any points in common, so your solution is there is none. It's the empty set. If you have two lines that do intersect in a single point, like right here, then you have one solution, and your solution is an ordered pair. So you will have an x and a y value together. We're looking for what is that point of intersection. And if you have two lines that end up being exactly the same line, then you have an infinite number of solutions. Well, I can't even spell it. Infinite number of solutions. So it would be your solution would be all of the points on the line. Now this point here wouldn't work, or this point here. Not every point works, but every point on one of the two lines would work. Okay, so that's what we're going to be looking for then, algebraically. There's a couple of methods we're going to use. The first one is substitution. So if you remember from geometry, the substitution property says that if two things are equal, so here we have if A is equal to B, whoops, and then let me get rid of that. There we go. Now I'll get the pen. So if A is equal to B, then when we see an A in expression, we can take it out and put in a B. So here was something you maybe saw in geometry. Let's say the measure of angle 1 plus the measure of angle 2 is 180. And if I know that angle 1 is equal to angle 3, then I can take out the measure of angle 1 and replace it with the measure of angle 3 because they're equal. So that's the substitution property. Okay, now try it on. I want you to pause this next problem and pause this and see if you can work this. And then when you get done, you can continue on and see what... I'm quite sure that you'll be able to solve this system by substitution. So when you did this, you probably looked at, maybe started with this one right here and saying, well, if 2 triangle is equal to 6, then that means triangle has to equal 3. And if triangle is 3, then 3 plus 3 is 6. So that means diamond has to equal 6. And then you're going to replace the diamond with 6 and the triangle with 3 to find out that the hexagon is 9. And then you can check it in here. 2 times 3 plus 2 times 6 is equal to 2 times 9, and it all checks out. Well, you're using substitution there. So that's what we're going to do on this problem. So a system of equations means 2 or more equations. So we're looking for what they have in common. So we want to know, are these lines parallel? Do they intersect in one point? Or is it the same line? All right, so to do it algebraically, what we're going to do, remember we're using substitution. If I take this second equation, because I see that I just have an x here, and it works really well if you don't have fractions in your answer. So it doesn't always work for all of them, but in this case it would work pretty well to solve the second equation for x. So that means that we have to get the x by itself. So we got to move over that 3y, because it was a plus 3y. On the left side, it's going to be minus 3y when you move it over to the right. So I've used this second equation and we've solved it for x. Oh, I got two equal signs for some reason. So now I'm going to take what x is equal to and substitute it in to the first equation. All right, so I've got 2. I take out the x and replace it with 3 minus 3y. And then the rest of the equation doesn't change. And I need all of the rest of that equation. I see now that I only have y's in that equation, so we can solve it for y. We'll distribute first. I'm going to combine like terms over on the left side. Negative 6y plus 5y is minus y. I'm going to move the 6 over, so we subtract 6 from both sides. Negative y is equal to negative 11, so therefore y is positive 11. So remember, if you have a negative in front of the y, you can either multiply or divide both sides by a negative 1. So we need to know what y is. Well, if we found a value for y, then that means these two lines intersect in a point, and the y is the y value of that point. So we only have part of the solution. We need to find the x. So now we're going to use substitution again, and we are going to take that value that we got here and substitute it in to this equation that we solved for x. So I'm looking for x. So x is equal to 3 minus 3 times y. So I take out the y and replace it with 11. I'm using substitution there also. So x is equal to 3 minus 33. So that means x is a negative 30. So the ordered pair, negative 30, comma 11, is the ordered pair of the point where those two lines meet. They cross at that point. So you could either write the solution like this as an ordered pair, or you can write it like that. Either one is going to be okay. All right, so that is substitution. All right, let's try another one. So take a look at these two equations. Which equation is going to be easier to solve for which variable? Well, because I just have a 1y here, this second equation then is probably going to be the easiest to solve for a particular variable. So I'm going to solve this one for y. Keep the y over here on the left side. Move the 2x over. So it's going to be 4 plus 2x, which is exactly the same thing as 2x plus 4. It doesn't matter how you write it. All right, and then we are going to take that and we're going to use substitution. So we're going to take this value for y and substitute it in the first equation, the other equation for y. So I just take out the y, everything else stays the same. So we have 3x plus 2, and in place of y, we put 4 plus 2x. That is equal to 1. So to solve it, you see we just have x's in this equation. So we've got to distribute that 2. So, well, we can combine the x's, so we get 7x. And then we want to isolate the x, so we're going to subtract 8 from both sides. And now we're going to divide both sides by 7. All right, so here again, I've got a particular value for x, so I know that these two lines intersect in one point. And we found the x value of the point. So now we need the y value of the point. So we use substitution again. We take this and we substitute it in to this equation because we're looking for y. Y is equal to 4 plus 2 times what our x value is. So 2 times negative 1 is minus 2. So it looks like y is 2. So these two lines intersect at the point -1, +2. So these are intersecting lines. They just have the one point in common. Okay, the elimination method then, let's try it next. So the goal of this is to eliminate one of the variables by adding the two equations together. Well, if you remember, the only way we can eliminate something, get it to add to 0, is if they are additive inverses of each other. So, oops. So let me click outside here again. There we go. So we're looking for additive inverses. So for example, the additive inverse of 2, if I want to make that 2 go away, is I add a -2. And if I have an x, the additive inverse is -x. And if I have a 3y, the additive inverse of 3y is -3y. Okay, so we're using that property then. So when you look at a system of equations, that's what we're looking for. So take a look here. I've got a 3x. Oh, sorry, I keep forgetting to grab my pen. I've got a 3x and a 6x. Those are not additive inverses. If I would add those two together right now, I would get 9x. They wouldn't cancel each other out. I look over at the y's. I get -7y, -8y. Well, same thing. So we're going to have to do a little bit of work here. The easiest thing to do here is eliminate the x's. I have a 6x here. So to get the x to cancel out, I need a -6x on the top one. Well, I already have a 3x, so I would just have to multiply that whole equation by -2. Okay, so let's multiply it and bring it below here. So we would get -6x plus 14y is equal to -20. Now, when I add those two equations together, the 6x and the -6x are additive inverses, so they are going to cancel. So I add now -8y and, oh, I'm sorry. Yeah, I add -8y and 14y together. So remember, this equation we already used. We rewrote it down here, so we're done with it. So when I combine here then, -8y plus 14y is 6y. And when I add 8 plus a -20, we get -12. Dividing by 6 tells us that y is -2. So these two lines also intersect in one point. I need to find now the x value. Now we can go back and use elimination again in order to get rid of the y's, but it's a little bit simpler just to take that and substitute what we just came up with, the value for y, and substitute it into one of the two equations. And it doesn't matter which one we choose. Because I already crossed out the first one, let's take the second equation then. So I have 6x minus 8 times y, but we know y is -2, so we're going to substitute in a -2 for the y. Now I can solve this for x. -8 minus times a -2 is plus 16. So that means we have to subtract 16 from both sides. So 8 minus 16 is -8. Then I have to divide by 6. Yes, you can write it as a decimal. I just like to reduce down that fraction. So if I reduce 6 by 2, I get 4/3. So -4/3, if you want to write it as -1 1/3, that would be fine also. So there is our point of intersection. If I write it as an ordered pair then, because on a graph that's where they would meet, those two lines, that would be my solution. So there we used elimination, but notice once we found this, then we went and did the second part of it by using substitution. Okay, now let's take a look at this one here. We want to use elimination on this one also. You could look at the x's and say, you know what, we can multiply the second equation by 4, but I think I'm going to force us to get rid of the y's in this one. So we're going to get rid of the y's. So in order for that to happen then, they have to be additive inverses of each other. I've got a 2y and I've got a 3y. So because I don't really want to multiply by fractions, what I'm going to do is just multiply the first equation by, not 6, I want to get a 6, by 3. And that'll give me a 6y. And then on my second equation, since I have a 3y, I'd want to get a negative 6y. I'm going to multiply by negative 2. So remember, you have to multiply everything all the way across, even the constant term, times those two numbers that you're multiplying. Okay, so on the first one then, we get 24x plus 6y is equal to 12. When we multiply the negative 2 through the second equation, we get positive 4x minus 6y is equal to negative 26. Okay, now look. Now these are opposite, so these are going to cancel. These are additive inverses of each other. I'm going to have to add the 24 and the 4, so I get 28x. And then I add the 12 and the negative 26, so I get negative 14. So when I divide by 28, I get negative 14 over 28 and reduce that fraction. So we get negative 1/2. Once again, I found an x value, so that means that they are intersecting at one point. So now we just have to find the y value that goes along with that x. So we use substitution and we plug it into either one of them. I'll take the top one this time. So 8x, I'm going to take out the x, put in the negative 1/2, plus 2y is equal to 4. 8 times negative 1/2 is negative 4. Remember, the 4's here now do not cancel out because one's a positive, one's a negative. They're on opposite sides, though. So I have to add the 4 over. So that means 2y is equal to 8. So therefore, y is 4. So that's my ordered pair. Now remember, in order for a point to be on the line, that means when we plug it in, we get, they equal each other, the two sides. So let's try it, plugging that in. So we're going to put the negative 1/2 in for the x, and at the same time put the 4 in for the y. So 8 times negative 1/2 is negative 4, plus 2 times 4 is 8, and I want to know, does that equal 4? And yes, it does. So that is indeed a point on the first line. Now let's substitute it in here. I want to take negative 2 times negative 1/2. Well, that will give us a positive 1, plus 3 times 4 is 12. And does that equal 13? Yes, it does. So you can see that this point belongs to both of those lines. So that's a nice little check then. So yes, that would be a common solution that they have, and that is the only one. Solve a linear system with many or no solutions. Okay, well, let's take a look at this first one. Let's say that we want to use substitution because I have just an x all by itself here. And so that first equation is going to be pretty easy to solve for x. So I need to move that negative 2y over. So we get 2y plus 4. Or you may write it 4 plus 2y. Then we take that and we substitute it in for the x in the second equation. Alright, so we get 3 times 2y plus 4. Now all we have are y's in that equation, so we want to solve for y, so we distribute. Combine like terms. And when I combine, oh look there, a 6y and a negative 6y. Those are opposites. I'm on the same side of the equation, so those are going to cancel. Well, that's nice, except for I just canceled out my y. I no longer have a variable in there. And what I have left is a 12 over here and an 8 over here. So when this happens, when the variables cancel, and your statement that you have left is false, that means that there is no solution. So think back to that first slide that we talked about. If there's no solution, that means they have no points in common. So that means then that these two lines are parallel to each other. So they have no points in common. All right? So there's an example of no solutions. Okay, let's take a look at this. Next one. 4x minus 10y is equal to 8, and negative 14x plus 35y is equal to negative 28. Well, let's use elimination on this one. So look at both of these. These are both kind of ugly. But like a 4x and a negative 14x. Well, I think what I will do is on the top one is first of all divide through by 2, because notice how all of those numbers are even. So if I divide through by 2, I'm not changing the equation at all. It's still going to be the same equation, but I would have 2x minus 5y is equal to 4. As long as we do the same thing to both sides, we're not harming anything. Now, notice I want to use elimination. So if I have a negative 14x in this equation, this one then I need to have a positive 14x. So now I'm going to multiply by 7. So that'll give me a positive 14x minus 35y is equal to 28. Okay, I'm going to bring this equation down and put it right below here. So negative 14x plus 35y is equal to negative 28. So not only do the x's cancel, but then so do the y's, and so do the constants on the other side. So now the variable's gone, and I have a true statement. So when I have a true statement, that means we have an infinite number of solutions. So what's going on here is that when I tried to rewrite those two lines, I got the same line. Because I could go through on this second one and change all the signs, like multiply by a negative, and notice that it's exactly the same as the first one. So we have the same line. Both of these two are exactly the same line. So our solution is all of the points on that line. Okay? So there's an example of an infinite number of solutions. Let's say we have this problem here. A music store. Oops, I got a phone call. Hold on. All right, so in this equation then, or in this problem, we want to set up two equations. And this talks about a couple of things. It talks about the price of these guitars, and it talks about how many were sold. So that's how you kind of think, how you break it up. So we have got electric guitars and acoustic guitars. So let's say that the number of electric guitars that we sell is going to be X, and Y will be the number of acoustic. Okay. We know that, let's start off with the dollar amounts. So we sold some of each, and we made $3,600.11. Every electric guitar that we sold, we got $479. So however many we sold, which is X, we've got to take times 479. So we've got 479X, plus we made some money on the acoustic guitars. We made $339 for every one that we sold. So 339 times Y will give us the total amount of money that we made. Okay, so in that particular equation then, we put all of the money together. Okay, in the next equation then, let's just talk about the guitars sold. So we sold 9 altogether. Well, if we sold 1 electric, that means we sold 8 acoustic. And if we sold 5 electric, that means that there were 4 acoustic. So that means that the sum of the electric plus the number of acoustic guitars sold was 9. So there are the two equations. So then at this point you decide, well, what would be the easiest way to solve this, elimination or substitution? And it's kind of up to you. Both are going to be fairly simple. Let's do elimination. If in this first equation I have 479x and I want to get rid of the x here, that means I have to multiply this equation by a negative 479. So we'd get negative 479x minus 479y, and then you'd have to multiply that 479 times the other side, and don't forget it's the negative, so it's going to change it. And when I did that, I got negative 4,311. You could try it on your calculator, make sure that's right. Now remember, we're combining it with the first one, this equation right here. So we're adding this equation to this one. So when we add them, the 479 x's are going to cancel because I have a positive and a negative. And then when I look at these two, I got a positive 339 minus 479. So I'm going to get a negative 140y. And then we want to combine the 3611 to the negative 4311. And when we add those two, we get a negative 700. So now we can divide both sides by a negative 140. And we see that y is a positive 5. So remember, y was the number of acoustic guitars we sold, and that is 5. So there were 5 acoustic. And then to figure out what the x, the number of electric, we substitute into one of the equations. Well, this one is going to be the easiest one to substitute it into. So 5 plus what gives us 9. So that means there were 4 electric guitars sold. Okay, so that is how you solve systems of equations. So now you guys get to try it. So I have 3 problems that I would like you to solve, and do those, get the solutions to those before you come back to class. And if you get stuck, then make sure you have a question for us to where you got stuck and what needs to be explained a little bit better. Okay, so once again, you can pause it here, but hope you have good luck with those, and we'll see you in class.